I believe it is recording right now. Yes. So, good morning, good afternoon, and good evening, everyone, depending where you are right now. So it's my pleasure to welcome you all on the second part of the Motorola Solution Meetup that is dedicated for artificial intelligence and machine learning for public safety. Before we start, I would want to inform you that this session is being recorded. So if for some reason it is not okay with you, then I'm afraid that the only option is to leave the meeting. But I really hope that you will stay with us. So on this part, we have two topics. One is the first one is the predictive bandwidth analysis of AI-driven video security cameras, where you will learn how to predict and allocate enough bandwidth so that our AI-driven cameras that requires precise bandwidth allotment in a field can perform the analytics at the edge. The topic will be presented by Mustaf, who leads the cloud application team under MSI, Video Security and Analytics Organization, and Wishwarap, our data scientist who works with system design tool team at Motorola Solution. The second topic would be video analytics for COVID-19 response. You will learn there how to evaluate, based on the video, the distance between people in a given area, also whether a person is wearing a face mask or not, and also how to determine elevated body temperature. This topic will be presented by Jehan, who leads the artificial intelligence group for MSI and developing mission critical AI solution for public safety and commercial markets. Each topic is planned for about 20 minutes presentation and then 10 minutes of Q&A. Please type your questions on chat so that presenters can answer them during QA session. You also can send your questions via email, and those questions will be answered as well. So I think that we could start with the first topic, which is the predictive bandwidth analysis. So, gentlemen, the stage is yours. Wishvaran or Mustaf, you can start.
Hello. Hello.
Yes, we can hear you.
Yes. So I'm going to talk about the system design tool. So this is a tool which is used by average loans partners and clients to design the camera system they want to use. So if you can see my screen, the partners and clients can go to the average loan system design tool and they can design their whole system. So you can enter the facility name and the camera settings. I can go to the place where I want to set up my whole camera system. Let's say I want to go to my university campus and I want to set up the whole camera system. So, and this is the main building of the university. And here I can go and add cameras. Let's say I want to add 3 cameras and I can place the camera over here and then I can also add storage to store the videos that are being recorded by the camera. Now, the SDT also allows us to tells us the amount of bandwidth that will be used by these cameras, and the amount of storage that is being provided by the server. So here we see that the NVR4 provides a 14.64 terabytes of storage, and this is equally divided across the three cameras. And we are using an H5A camera. And the model predicts the amount of bandwidth that will be used, and accordingly, we can also see that what is the maximum possible bandwidth, that is 300. And the bandwidth here changes according to the image quality we want to select, and the image rate, the scene types, the keyframe interval. So all these factors affect the bandwidth. And it is important for us to predict the right bandwidth so that the whole system can run smoothly. If the system is not able to run smoothly, then it won't be good for average loans and average loan customers. So I will go back to my presentation. And so the main idea of SDT is to help the clients and the partners to design the right system so that it can work smoothly. And why bandwidth modeling is important? Bandwidth modeling is important because we want to tell the customers what is the right server size they need and what is the right bandwidth connection is required. Now, each of these servers are very expensive. So if we suggest the wrong server size, it may be costly for average loan to compensate the customers. Okay. Now, once we know that why this bandwidth model is important, uh, we need to see how we come up with this bandwidth model, how the data is collected, how we train the model, and how we implement the model in SDT. Now, uh, just as we saw the SDT web application, the camera has many settings like image quality, image rate, keyframe intervals, and if we calculate the total settings, can be 2 million possible combinations of settings, and it is not possible to collect those many data points. So we start with a small set of input settings. We collect the data for those settings, we examine the data, we compute the model, and then we publish it in SDT. Now, as a part of the SDT team, my project had two parts. First was data validation to check whether the data that is being collected follows the expected trend or not, whether there are outliers or whether there is noise. And the second part is to build a good and an accurate model. Now, previously, since there was not a particular data scientist who used to work in this, so the pipeline was not very smooth. And initially, what used to happen is that we used to collect the data, and there was no automated data validation. We just used to go directly to compute the model, and then we used to see that the model is not performing well. And then there was a lot of back and forth between data collection and after the model is tested. But now with automated validation, what we do is we can check the trends in the data, we can build the model, we can check the trends of the model and compare everything. So how this data is collected? So we have an input script which contains a few camera settings, around 500 to 600 different camera settings out of the 2 million possible camera settings. Then we set up the camera in a lab and we point the camera towards the screen. The output is generated in the form of a CSV file, And then we have the validation script, which checks all the trends in the data and tells us whether the data is following all the trends or not, and whether the data is correct or not. So earlier, before I worked on this project, the challenges was that there was a lot of back and forth communication to validate the measurements in the model. And earlier, all the measurements were finally it was outputted in the CSV file, and the validation was done on an Excel spreadsheet. And what we actually did was make a single plot to check how the data is distributed. And most of this validation was done manually, and there was no proper pipeline for the data science work. Also, each of these measurements require a lot of time. Now, let's say before for each camera scene type setting, we used to take 660 measurements. And this to take this 660 measurements, it used to take 10 and a half hours. And let's say if we have one camera and six different scene types, and each camera has three different sensors, that will be around 190 hours to take one measurement, to take the measurements without any rerun. So that was a lot of time to collect the measurements. And also the model which was there previously was not accurate and didn't follow the expected trends. So as I said before, my project has two parts. The first is the data validation and second is the model building. So we need to build a model which is accurate and which follows all the expected trends. So first I'll go through the data validation part and then I'll talk about the models. So previously we just had simple spreadsheet and we used to plot we used to see the distribution of the data for different settings. But now we use different uh, visualizations to validate our data. So as we saw in the SDT web application, the factors that affect the bandwidth are scene detail. So scene detail has three different levels: high, medium, and low. Then there is motion in the scene. So there's either 1% motion or 5% motion. The camera resolution, the image rate, image quality, keyframe, smart codec. So smart codec is basically a compression technique. WDR manages the amount of exposure and lighting in the image. The format we want to save the video, and flicker rate. So So our data set consists of a lot of different settings like low 1% scene type, low 5% scene type. We have different uh, camera sensors, 2 megapixel, 4 megapixel, 8 megapixel for the H5A camera. Each of these cameras have these many scene type settings. And then there are further data sets which account for smart codec, idle scene mode, and different compression techniques. So now, rather than just building one plot in a Excel spreadsheet, now we use Python to generate plots and to see the trends in the data. So let's say if you want to check how, if we change the quality of image, how the megabits per second that is being produced is changing. And this red line tells the median value across the different quality settings. And the blue dots are the distributions. We can furthermore, compare, let's say for image rate, we can compare for different scene types. So we expect that the low 1% scene will have lower bandwidth as compared to the low 5% scene. And then the medium 1% scene will have a lower bandwidth as compared to the medium 5% scene. This is a plot for smart codec. So we can see the distribution of the megabits per second for different camera resolution and different camera settings. And we can see that it is not always that the data will follow the expected trends. It may be possible the data doesn't follow the expected trends. Now here in smart codec, we expect that as the level of smart codec goes up from low to medium to high, the bandwidth should go down. So for this particular resolution, the bandwidth goes down, but that is not the case for other resolutions. So this was all about the data validation. And now I will go ahead and talk about what are the different models I have built so that we can predict the bandwidth more accurately, and the model should follow all the trends that we expect. So previously we had a simple log linear model, and the problem with this model was that it didn't give accurate results for non-default settings. So there are certain default settings, but for non-default settings, this model didn't work well. And secondly, the absolute mean absolute error for this model was 1.5 megabits per second, so it was not very accurate, and also it didn't follow all the trends. Now, the current version of SDT has the model which I've built, and this model is like a student-teacher model. And here the teacher is the random forest model, and the student is a log linear model. Now, why did I build a student-teacher model? It is because random forest doesn't always give a unique value for all the different settings, and it at times what happens is that it averages the values for certain settings and gives the same value for them, but we required a unique value for each setting. So we had to make a teacher and a student model where the teacher is a random forest model and the student is a log linear model, and we use the student model to make the predictions. Now the advantage with the random forest model is that the mean absolute error was zero point 0.9 megabits per second, which is lesser than the linear model, and the R squared was 95%. So the model was able to learn the data very well. And once it learns the data well, then we were able to use this model, generate more data, and then build a linear model on top of that to make the predictions. But this whole setup is a bit complex, uh, but it solved all the problems which we were facing before. It followed all the trends. Like we expect that with quality, the bandwidth should decrease. So we see that the bandwidth is decreasing. With keyframe, the bandwidth should decrease. We see that the bandwidth is decreasing with keyframe. With image rate, the bandwidth should increase. And with primary resolution, as it increases, the bandwidth should increase. So the model follows all the trend. The model is more accurate, and the model also predicts better for non-default settings. Another challenge that was there before is that taking all these measurements is very time consuming. So I wanted to check the accuracy of the data versus the number of data points I required. And I saw that with lesser number of data points, I can achieve the same accuracy. Hence, we can save a lot of time while data during the data collection process. So here we see that in total, I had around 1800 data points, and we see that around 1300 data points, at around 1300 data points, I get the same accuracy. So I don't require the extra 500 data points to achieve that level of accuracy. So as I mentioned, all the improvements that we achieved through this model. But this model was not, it was a bit cumbersome model, and So, and since we have a regression problem, so we came up with the neural network model. This neural network model, which I implemented, was far more accurate than the random forest model. So the mean absolute error was only zero point 0.7 megabits per second, and it was more simple to generate because based it was based on the raw data, and we didn't have to first train a teacher model, generate data from the teacher model, and then train the student model. We could simply use the raw data and then you generate the model based on the raw data. Also, the student teacher model was the size of that model was large as compared to the TensorFlow model, which is very compact. So it can be easily implemented into the system design tool. But there was some challenges. The challenge was that the raw data doesn't always follow the trends and may contain noise. So it may be possible that the raw data doesn't go down as we decrease the quality, or the bandwidth doesn't always go up as we increase the image rate. So this may be due to the noise, or that is how the camera works. Secondly, there are too few data points, and we don't have values for all the different settings. We have a very small data set. So what happened was that the model was not able to follow all the trends, and we needed to enforce these trends in the neural network model. Like say for quality, we expected the quality to go down, but we see that from some higher values of quality, the value of bandwidth is going up. So the model was not able to follow all the trends. So to solve this problem, we came up with something called as a custom loss function called the point-wise loss function. Now, what this loss function does is it has two parts. The second part is the mean squared error, which it tries to minimize. And the first part is that it takes the gradient of the uh, uh, it takes the gradient of the output with respect to the input. So this part makes sure that the model is monotonic. So and this helps us to enforce the trends in the neural network. So when I went ahead and implemented this custom loss function, we saw that we saw that the model followed the model now follows the trend. So for quality, the uh, bandwidth reduced as we increase as the quality decreased, the bandwidth also decreased. And this is the model performance. So as we train more number of epochs, both the test and the training area decreases. So in this whole project, we added the value which we added was that we reduced the amount of back and forth that used to happen before, because there was no proper data science pipeline. And so there is automatic, the whole data validation process is automated, and we need fewer data measurements to we need fewer data measurements to fit the model. So it saves a lot of time. And since it saves a lot of time, we can implement this system sooner so that clients can use it sooner. Also, with respect to the model, now the model is more accurate. It follows all the trends. It predicts accurate values for non-default settings, and it is easier to use and implement. Uh, so if you guys have any questions, you can please feel free to ask.
Thanks a lot, Viswara. Yeah, this is really a huge benefit to our team and to our sales force. it's been in a journey to get to this point. We've had lots of different measurement issues. I'll give you a few examples around Dallas Police Department and another few installments that we have low bandwidth areas that with this what type of accuracy would have been very beneficial for us, and it's going to prove a lot more value as we enhance this and as we add it to more and more cameras. Thank you so much, Viswara, and thank everybody for attending. Back to you, Kamil.
So we have a question: is motion on the scene a static parameter or calculated one? So it is a static parameter, yeah, because we actually have 3 different levels of motion, which is the 1% motion, the 5% motion, and then we have the idle scene mode with no motion. So how it is done is that when the camera is set up in the lab, it is pointed to a screen, and in the screen we have these 3 different levels of motion, and the screen usually has a fan which moves. So if the fan is moving slowly, we say it is 1% motion, and if the fan is moving at a higher rate, we call it at a 5% motion.
Okay.
Did it answer your question?
Yeah, that was my question. Thank you very much. Yes, definitely. Another question I have, do you apply any margin? So no matter how accurate your calculation is, there still is some margin in case you miss the trend or something happened.
No, currently we are not applying any margin. No. So we what we do is once we fit the model, I test it in some test dummy data sets, and once the model is implemented in SDT, it is again tested. So, and if we see that the trends are not followed, then we go back and we have to retrain the model or make some tweaks in the model so that it follows all the trends.
Okay, thank you very much. So I encourage everyone to type your question on a chat. At the end, if time allows, and there are any unanswered questions, we can address them at the end as well. Okay, gentlemen, thank you very much. Then, so that was really nice to learn that stuff and see how you are doing it. So I think that we could move to Jehan presentation related to the video analysis in COVID-19 times. So Jehan, if you can share your screen and you can start.
Thanks, Camille. All right, can everyone see my screen?
Yes, we can.
Okay, so this is actually a good segue into this talk. So just a little bit of context before we started, because I'm not sure it was mentioned. You'll see names like you'll see Avigilon mentioned prominently, not only in the last presentation but here. So as Camille mentioned, that we have a video security and analytics organization at Motorola. It's our video organization essentially, and then there are a number of kind of brands under that, and Avigilon is one of those brands, primarily in the fixed video surveillance space. So when you see that term, it's essentially one of the family of companies under the Motorola Solutions brand in the video organization. So anyway, so we talked a little bit about setting up cameras and using the tools that have been built in MeetUp's team to be able to help customers do that effectively using machine learning. I'm going to talk a little bit more, and actually same cameras that we're talking about, but a very specific use case, which is video analytics for COVID-19 response. So before I start, let me give you a little bit of an overview of the team and kind of the work around AI that happens at Motorola. Actually, last time we had someone from our team, David Calico, present on automatic speech recognition and transcription. The way this kind of fits into the group of things that we do, and today we'll talk about video analytics. But under the AI team, these are kind of the areas that we work on. So across video, speech and audio, language, and then there's a bunch of services and platform stuff that we work on to essentially enable those solutions in products and services. So this is kind of how the team is structured, and today we'll focus very specifically on video analytics. It's a lot to fit into 20 minutes because it requires some background knowledge and understanding how some of the stuff works. So please ask questions. I've intentionally kept the slides minimal in terms of text, but I'm happy to answer any question if you have it. So feel free to just keep asking questions in the chat as I'm going along. You don't have to wait till the end. Okay, so as I said, today we're going to talk about video analytics, but we're actually going to talk about a very specific type of video analytics. And in terms of the data source, we're going to talk about fixed video cameras. So Motorola Solutions, the video organization in general, a large portion of the work we do is for fixed video, but we also have mobile video sources. So body-worn cameras, dash cameras, mobile applications where video is captured. So even though I'm going to focus largely today on fixed video, a lot of the video analytics work that we do in the team and in the company also affects the other types of video which have different considerations, because in that case, not only obviously are your subjects moving, but your camera is moving as well, which affects things like tracking, object detection accuracy, and things like that. So keep in mind that today's talk we're going to focus very specifically on the fixed video problem. Okay, so one thing I want to point out, and I think this is unique to how we as a company approach AI and computer vision in specifically for video, is we look at it as a distributed problem. So you heard about our cameras. I'll talk a little bit more about them later. So we can do some level of computation at the edge on cameras, which obviously is beneficial. You can save that compute cost elsewhere, do it at the edge, allow you to trigger alarms and rules in real time. But we also distribute machine learning across these other two buckets. So servers, obviously, so for video management systems, customers store video on premises on servers, but we also do a certain amount of machine learning on the servers as well. So many of our servers have GPUs that we sell as part of our solution, and we execute different machine learning models there. Increasingly now, we're also focusing on doing more AI in the cloud. So think about it as a distributed system where you're trying to achieve a goal end to end, and where you actually run a particular model, we can basically optimize that for the use case. So in some sense, it might make sense to run something on a camera, but downstream, you might run something in the cloud or on a server based on that information from the camera. So think about like the edge as being essentially a discriminator. So you essentially look at a scene and maybe you identify within that scene what is important. Maybe it's a particular object or an object class or a region of interest. And then we can take that region of interest or that object, say as an image or a part of an image, and run an additional machine learning model downstream to say classify that, for example. So we really use this to our advantage because we have a complete end-to-end solution. We don't just make cameras, we don't just make servers with GPUs or offer a cloud service, we do everything. So this gives us an advantage in the solutions that we build, primarily because a lot of the time compute is limited, right? So even if you look at something like the cloud, it's potentially unlimited, but you're paying for it. So it isn't. So you have to be able to optimize your machine learning models to be as efficient as possible. And beyond that compute budget that you have, you can also distribute it amongst these three things, which allows you to do a lot of interesting things that you couldn't do on any one of these platforms by itself. Okay, so as I said, computational challenges, right? So obviously, edge computing, we have various SoCs that we use that we run machine learning models on. They're going to be very limited in terms of compute. They have to fit on a camera. They have to have a certain, cost metric associated with them. Just to give you a point of comparison, something like a P1000, which is a fairly old NVIDIA GPU class, can support something like 200 streams of video from 200 cameras. And it's even that, which is, you know, a full GPU is many times less powerful than something like a Tesla class V100, which is commonly used for machine learning today, especially in the cloud. And if you look at the power difference, it's huge. You're talking about a few watts on a camera versus, you know, hundreds of watts on something like a V100. So this is the challenge which we develop. So it's not just about, you know, building a particular model to achieve a goal. You have to actually make it fit within these computational limits that you have on specific types of hardware. And there's an entire, you know, amount of work that happens there in terms of optimization of models and, you know, a whole bunch of work in that area. I'm not going to get into the details, but just be aware that this is the challenge that we generally face when we're doing video analytics, is that we have to kind of deal with these limits no matter where we're actually deploying a particular model. Okay, so just to give you a sense, what does it actually mean? So what are the kind of the basic types of analytics that we run on our cameras? So obviously object detection, you want to be able to detect objects, so bounding boxes around, you know, things of interest, people, vehicles. We also need to be able to actually detect objects at fairly small sizes, which is obviously a challenge. And then also in terms of the number of objects we need to detect, some of these are fairly dense scenes. And so you have to have an object detector, and then you have to solve the tracking problem as well. So essentially, when you have an object that you detect, if you can do detection basically every frame, you don't need to have a tracker, right? But detection is expensive from an inference, you know, cost standpoint. And so what typically systems like this do is that you do detection every X frames, and then you track in between. So there's a combination of tracking methods that you use, you know, from correlation-based tracking to, you know, more traditional tracking, like using Kalman filters and things like that. I'm not going to get into the details, but just to let you know that on the camera itself, the basics that we do are basically detection and tracking, because we want to be able to understand the scene in terms of the objects that are there and how they're moving, and, you know, hopefully do a good job of tracking them so that we have unique identifiers for those objects. There is some level of classification that also happens on the camera, but I'm not going to get into that now. But suffice to say that this is also something that we do in a distributed manner. Like, we don't only do it on the camera. So think of this as this is the basic kind of building block of where we start. Okay, I see. I'm going to answer questions as we go along, because I think it makes more sense to do that. So I'm not going to say what model we use, but we don't use like an off-the-shelf model for this. This is a custom network that we built for our cameras. All I'll say is that it's based on a single-shot detector. So if you know what that architecture is, we've basically built it from scratch. The reason we built it from scratch for this purpose is we really have to optimize many things to work well on the camera. So everything from, you know, anchor boxes to, you know, how much range we need to have on our detections and things like that. So we typically have our own network that we build and we maintain for this purpose. Okay, so let me get into, okay, so that said, so think of that as like the basic raw materials, the basic ingredients that we need to enable, you know, any kind of video analytics. And specifically this year, as you all know, it's been a challenging year for everyone, where, you know, this pandemic was completely unexpected. I know our teams, we didn't really have any plans to build these solutions this year. So obviously this was something that was more reactive than it was planned in terms of kind of a roadmap activity. So when the pandemic broke out, one of the things was our customers who use our, you know, video products had different needs. And so let's start with the actual human needs, the things that they needed to be able to solve. So there were three main things, right? One is in workplaces, they want to figure out what's happening. What's the situational awareness picture to maintain, you know, compliance. Compliance is important. You have employees coming into the building. You need to be able to make sure that, you know, they're not sick. And if someone does get sick, you want to be able to figure out who they interacted with so that you can let them know, so that you can keep the rest of the workforce safe. One of the other things is a really important factor is providing decision support, not only for employees, but building managers and, you know, other teams in the building to be able to make a decision. So typically these days, if you don't have to go into work, you know, kind of every day based on your role, you make a decision on whether that risk is actually something that you want to incur when you go into work and you have to do something. And we want to provide data to these organizations so that they can make an informed decision about it. And that risk is a combination of like the individual, how they're commuting to work. It's a combination of what's going on around in the building, and then more importantly and more relevant to these video analytics, what is actually happening in the building. Are people congregating, in groups? Are people wearing masks? Because that's definitely a policy that needs to be enforced. Do they have an elevated temperature when they enter the building, which would mean that they would be at risk? So we decided to try to tackle this problem using computer vision. This is not the only way, right? And by no means is this supposed to be an extensive solution to solve, the COVID problem. The COVID problem is largely unsolved on many different fronts. But one of the things that we tried to do here is, since we are responsible for video analytics on our cameras, can we use some of that information to provide information to organizations that can keep their employees safe? And you'll see that little dashboard on the side. Actually, I'm glad MeetUp's on the call. So it's actually his team, which is the Avigilon Cloud Services team that deploy this. This is essentially a dashboard that rolls up all of the analytics metadata that I'm going to talk about today into a view that allows someone to very quickly see trends and insights on how these things are happening. What does my face mask compliance look like over the last, X number of days or weeks? How many social distancing violation events are happening? So on and so forth. So let's kind of dive in. I see there's a question about fixed cameras and the resolution. So these cameras, you can definitely, it depends on the camera. There's a pretty wide array of cameras, but if I think about our H5 platform, at least for the purposes of this, consider like a fixed scene. Some of these cameras do have, things like PTZ capability, which is, have the ability to zoom and so on. But assume that all the solutions I'm talking about, you don't need to zoom in to be able to actually execute any of these machine learning capabilities. So assume that for this talk for now. Okay, so we'll start with the first one, which is social distancing. Now, social distancing is just an application of this, but the more general problem is actually a camera parameter estimation problem. And first of all, I'll state this is not machine learning. So as cool as it is to exploit all the different ways machine learning is used, there are still some old fundamental techniques that are still very valuable, and in general, you use them to solve the problem that you have in front of you. So there's a classic camera parameter estimation problem. So to kind of set this up, the general problem is that you want to translate from 3D world coordinates to 2D pixel coordinates. So that's what the camera sees. So if you want to understand, for example, real world distances, you need to be able to do that translation. And that to do that projection, you need to understand the camera parameters itself. So things like focal length and sensor size. Essentially, you want to be able to estimate the height of the camera, because that is not always a given. Customers go install these cameras in different places, but you need to be able to figure out these parameters to be able to do this mapping. Now, if you had all of the parameters measured by a human, then this is easy. But typically, we are missing one or more of these parameters, in which case it becomes an optimization problem that you have to solve. And this is a classic problem, but there are some very unique ways we solved it that I cannot get into in terms of, some of the specific things that we did. But I think in terms of just understanding the problem, essentially estimating what is called the homology model, and from, learning the average height of a human in the scene, and using that to essentially set up a mathematical model to be able to figure out basically real world coordinates for any object that you see. So you'll see on the right, like, it's not just distance that you can figure out when you know that mapping, between pixel coordinates and real world coordinates. You can figure out, for example, is something too large? Is a scene too busy? And in this case, are people too close? So essentially, what I talked about last time is our video analytics operate on the basis of, we generate metadata with our models, and we have essentially a rules engine that has a bunch of rules that we can execute for certain events. In this case, the event is, if someone is within, say 6 feet of each other, trigger an alarm. And so having this projection and having these real world coordinates available to us means that we can do a pairwise comparison between the coordinates of two objects. That's fairly straightforward. You can do that in an optimized way to run it faster, but essentially the problem is relatively simple, in that once you know 3D coordinates in the real world, you're able to actually estimate in real time the distance between people and then generate alerts so that people can look at that information aggregated, or they can look at it, kind of as a real-time alert and take action. And I go back again to the real human problem that is being solved here, what a lot of companies, a lot of schools, organizations want to know is there anything from a planning standpoint in my building that is causing people to have these social distancing violations? For example, there might be a very busy conference room that only has a single hallway leading to it, in and out, in which case people are going to be within 6 feet just inherently. So understanding these statistics in a dashboard like I showed you before helps building administrators and other folks understand that, hey, this is a choke point in our building. People are going to come too close, and I should probably do something like maybe distribute the traffic away from that conference room, or set some guidelines so that people can have a more systematic way to enter it and exit it without having to cause these kind of violations. So it's all about providing data for decision making and providing good data for decision making. So this is really a geometry problem, which I think is interesting because everything these days is so much about machine learning and deep learning. And in fact, the other solutions I'm going to talk about are very much based on that. But this solution in particular is not a machine learning problem. It's a optimization problem that essentially converges based on the scene that it's seeing to be able to estimate these parameters and then eventually provide these distances. So moving on, okay, so face mask compliance. So in essence, right, at a very basic level, this is a classification problem. You can give, a machine learning student or anyone this problem and say, okay, I have a bunch of faces. I want you to build me a classifier that tells me if I'm wearing a mask or not, right? Sounds straightforward. I collect some data. I build a classifier to be able to do it. Seems pretty easy. But actually deploying a solution like this out into the market and making it work in all different scenarios is actually very, very challenging. There are a number of different reasons this is challenging. Not at the very least, it's also like on the right, you see there's a bunch of masks that you see there, right? So obviously there's not one kind of mask. It's you cannot assume that everyone is wearing like a surgical mask. People have masks that have faces printed on them. You can see the gentleman in the top left there has a mask that actually has a face. There are masks that have transparency in the middle where you can see part of the face. There are all kinds of weird and interesting face coverings that come up today. So you want to make sure that your model actually works with all of these things. It's actually a fair challenge. And then the other challenge is, as I told you about how specifically about surveillance cameras are mounted, they're mounted in different places where you get different angles, different shots of people's faces that make this problem actually fairly challenging to solve. So let's walk through the actual basics, like basic problem of solving this. So as I told you at the start, you have you potentially have a camera that is doing things like object detection and tracking, and it's detecting a bunch of different objects and object classes, right? Here, the model is really interested in human faces. So based on those detections that you get at the edge, you have to actually figure out, okay, what is the right face, the best face for that particular human? And then you have your classifier essentially look at that and basically break down some facial attributes and do a classification result on that and provide a result back which essentially tells me this person is wearing a mask or they're not wearing a mask. If they're not wearing a mask, you can do different things. Again, it can be event-based, there can be an alarm, it can be aggregated from a statistical standpoint. But a lot of the challenge has to do with actually making this work well. And there are a number of features. You can't just design the classifier in isolation. You need to make sure that you can deal with, for example, different angles, different poses of people's faces when you get them. For example, if you have a side shot of someone's face, or even something that is mostly the back of someone's head, it doesn't matter how good your classifier is, it's unlikely that you'll be able to actually give a high confidence result if the person is actually wearing a mask or not. So there are different parts of this system. So for example, one of the things that we do as part of our object detection process is doing face detection, which is once I have a human detected, I want to be able to capture their face. So that's a specifically trained model that does face detection. Now I have a bunch of face candidates, like essentially a bunch of image regions where candidate faces. Now I'll have more than one face for a particular person, Then the problem is, okay, how do I pick the best one? And best is, it really depends on what you're trying to do. But typically, in order to make a good result, a good classification result, you want to have a front-facing, a more frontal-facing view of that person's face. So we have different algorithms that also run over those images and determines, okay, what is the best face candidate I want to pick? Okay, once I have that candidate, now it's a more traditional classification problem where you try to estimate, you obviously you set your thresholds and you try to estimate based on what you're trying to do. Here, the priority is we want to actually detect when people are not wearing masks. Not that is the most important thing when you're thinking about kind of precision and recall here, is that you're really thinking about how can I be very, very confident when I alert someone that a person is not wearing a mask. And so you tune your classifier that way. And so the way you solve this problem is actually, just like most machine learning problems, a combination of data and algorithms, right? So I'm not going to get into details about the specific model that we used and how we tuned it. Suffice to say, everything I said before still applies. It needs to be lightweight enough that it's not, the feature backbone that it's using can't be super expensive, because we have to run this along with a bunch of other models in the same place on a particular server or in the cloud. So we need to balance that. Secondly, from a data standpoint, we need to be able to account for all these different face coverings. So one of the things that we did actually is we leveraged synthetic data quite a bit here. So think about the fact that you can do, most machine learning problems, you do some type of data augmentation, right? So you can do different things with your source data. You can, kind of crop it differently. You can change, for example, characteristics of the images. In this case, changing the color, the hue of the masks, the positioning of the mask on the face. Because remember, right, it's the classifier in this case is looking for different facial attributes in the face. So things like, if you're familiar with landmarks, so each face has, a bunch of basic landmarks on it that is used for a bunch of different things. But these landmarks are kind of a map of your face, right? And so using those to basically see how the mask is relatively positioned is a good way you can build a classifier to do certain things well, especially this kind of a task. There are lots of other things you can use. There are lots of different networks you can use, and how you actually initialize the weights for these classifiers is actually one of the things we had to actually very carefully tune. But in general, it's a very straightforward problem, like at a high level, which is build a classifier to figure out if someone's wearing a mask. But given this entire end-to-end system and the fact that it's working in real time in a distributed manner, making it work with high confidence is actually a very challenging problem, especially with the diversity of masks that you have. So I would say, like, in summary, there's basically two things: data, and then there's the algorithms part, and you have to solve it with both of these tools at your disposal to be able to get a well-performing result. So finally, I'll talk about a slightly different solution, which is actually, it's a hardware solution and a AI solution together that is solving the problem. So elevated temperature detection is something that we offer today, and the components are basically, there are two hardware components. One is a camera, and very specifically a thermal camera. And then secondly, we use something called a black body. So a black body is essentially a piece of hardware that gives you a temperature reference, because remember, you're measuring the temperature of things using thermal data, and you want to be able to understand relatively, you want to have a relative temperature guide, right? And this is what a black body actually does. So the black body needs to be in view of the camera. It needs to be marked by the user during installation. Now, we can auto detect this black body as well, but in general, you need to know where it is, because when you do the temperature measurement, you need to kind of use that black body as a reference. So these are the two hardware components. On the AI side, we actually, things we need on the camera to be able to do this, again, we need face detection, because as it turns out, the best place to measure temperature on a human face is something called the inner canthus, which is your inner part of your eye. And that spot is very key, because to get an accurate measurement using a thermal image, especially when you're talking about different resolution of images and different fidelity, like 16-bit versus 8, it's actually fairly tricky. There is a range of error that needs to be accounted for. And so if you're talking about an FDA deployed solution, which this currently is not, it has to be within half a degree. So to do an accurate measurement, number one, you have to detect the face accurately. You have to track that face to some degree, and then you need to do an accurate temperature measurement. And this is, kind of key to what we do. And again, this is another like trade-off problem. So it's the detector is not perfect, right? So you're going to have errors in your detection, but you can use this, the temperature measurement itself, and specifically detecting the inner canthus area to kind of offset some of those errors. So it's really like everything that you do here is kind of a trade-off. If you had a perfect face detector, or you had a perfect tracker, a perfect way to measure temperature, this problem is much easier. But in reality, this is not actually true. So you need to be able to trade off between those different components to be able to kind of figure out how can I get an accurate, temperature. And there's a lot of variation here. And we essentially trade off these things to basically filter false positives. So we can filter false positives based on temperature. Imagine someone holds up like a hot cup of coffee, for example. That's going to be the hottest part of the image from a thermal standpoint. If you're analyzing image data, clearly that's not what you want to measure. You want to make sure you're taking a measurement on the person's face and not, measuring a coffee cup, for example. So presence of this canthus area is very important. The size is important. And then if you think down the line, there are lots of other things. For example, glasses, right? Where you don't have IR passing through those things. And so people have to take their glasses off if you want to be able to do this measurement. People are wearing masks. Can our face detector deal with masks? And the answer is generally yes, but these are other variables that you have to account for if you're solving a problem like this. In many cases, a lot of the machine learning problems that we solve, they're very, analogous, like academic problems that are well understood. But when you're actually trying to solve it in a real product, there are a lot of variables that are outside your control. You don't have the right data. There are a lot of variations in how, what type of images or regions that you're processing, and you need to trade off, and you're compute limited. So if you think about, something that you would learn, to do an exercise, say, for example, something like a Kaggle problem, right? Where the problem is very well specified. You have a data set, you have a very clear metric that you need to kind of hit. When you're trying to solve problems like this in the real world, a lot of those things are not ideal. And so you have to deal with it and still create a good enough solution that, it's acceptable for customers. And so, the general theme of all of these solutions are, you have to be able to trade off between the different things that you have, whether it's compute, the accuracy of the different models, and the confidence and tuning the system end to end to be able to, provide, a good result. So those are the three solutions that, kind of like went into our kind of COVID response. And this is something, it's not just my team, it's like all of there were multiple teams at Motorola Solutions and Avigilon that worked very hard on these features to get them out the door. And actually we managed to get these features out from not having planned for this at the start of the year. In something like 3 or 4 months, we were able to get out well-performing solutions. And you can see one of the excerpts from one of the IPVM reviews on this feature. So IPVM is a very large site, which is kind of one of the prominent sites in the surveillance industry, which tests a lot of computer analytics capabilities from many manufacturers. And many of our solutions have been reviewed by them and had very, very favorable reviews that are, best in class or very close to it. So we're very proud of kind of the work that we do in general between, AI, engineering, product management, everything that we do in terms of putting out solid products for our customers. But just understand from a machine learning perspective, this is not easy. You have to kind of deal with kind of an imperfect problem that you're trying to solve and figure out how you can solve it. So that would be my, one takeaway with some of these solutions. I'll go through some of these questions that I haven't answered, but I wanted to preempt some of these questions because every time I talk about something that our team is doing or, AI at Motorola, I get these common questions. So I decided, okay, why don't I just get ahead of it and put a few of these on here. I'm happy to go into any kind of detail you want if you have other, more specific questions, but that's basically the gist of the talk. I'll go through some of these questions here. So let's see. How accurate should it be before it's deployed? That's a very good question. So typically when we deploy a solution, what we do is we work very closely with product management and QA. And what we do is we essentially decide and gather a real world data set. It's generally from our internal sites. So we basically put together a bunch of images / videos, depending on how we want to test. and we set ourselves a bar as far as, you know, the relative accuracy. So typically for things like this that generate alerts, the important thing is the false positive rate. You can't have a false positive rate, you know, that is too high. Otherwise, it becomes annoying for the customer and they end up ignoring it. And so typically, many of our analytics, especially in the fixed video space, have, you know, very, very good false positive rates compared to our competitors in the industry. And you're generally talking about, you know, false positive rates that are under 1% in general. But I can't give you like a specific answer because it really varies based on the specific use case. But typically, we try to minimize the false positive rate for things that are alert based. Now, if you think about things that are more like statistical in nature, like dashboards and aggregated insights, there you may not care as much about the individual like false positive rate, you know, precision and recall of a particular model, because you're actually, what the customer is interested in is clustering all of that data together and understanding like a trend, in which case you have more room to work. But anything that is event based or has an alarm associated with it, false positive rate is the single most important thing, at least in the surveillance industry. Can we detect neck jerk gestures and sneeze particles to identify if someone is sneezing? I'm sure we can. It's not a problem that, you know, we've had to solve to this point. But I'll say like the COVID problem is a very interesting one. So it's not just computer vision. That many of you might have seen that there are researchers all over the world that are solving this problem in a lot of different ways. So for example, audio is another very interesting modality in which to see if there are features and signals that indicate if someone may be a candidate for being, you know, having a positive COVID test. Now, remember, right, we are not diagnosing a medical condition here. What we're doing is we're trying to provide data that gives some insight that someone can take some action, actually take a proper temperature reading or whatever to be able to diagnose if someone is actually COVID positive. But there are many ways that you can actually do this. So you can look at things like lung capacity. So you have someone speak into a microphone and kind of look at that. There's research that kind of looks at, can I look at their essentially the audio from this person and see based on, you know, their breathing patterns or, you know, speech, can I actually pull out enough features that gives me more confidence? So I'll say many things like this are multimodal. We want to get as many pieces of information from as many different modalities and apply different techniques to that data and figure out a high confidence result. So that said, that's the conclusion of the talk. If you have questions about any of it, any specific thing, I'm happy to answer it.
If not right now, then definitely you can. Oh, there is one from Robert.
Do you face in practical applications need of coordinate transformation weight information on the camera environment? Actually, yes, that's actually a very good point, right? So one of the advantages that we have is we manufacture our own cameras. So we have actually good knowledge of many of these camera parameters, including, you know, specific hardware to be able to detect things. For example, if you have a IMU or an accelerometer on a camera, you can figure out camera tilt, right? So this is one of the advantages we have. That said, not all of our cameras actually have an IMU on board. So you have to estimate it. So basically, there are many cases where we don't have all of the parameters that we need. So a one parameter problem is obviously an easier optimization problem to solve than when two of those parameters are missing. So eventually, when we have to support, you know, third-party cameras, we have to solve that optimization problem. So there's definitely practical applications where you need to be able to do this parameter estimation where you don't have all of the information, and it becomes a harder optimization problem to solve, but it is solvable. Like Camille said, if you have any other questions after the fact you want to send, let me know. Send us questions on.
Yes, definitely. MeetUp at Motorola.com. You can send the questions, and we are glad to answer those questions as well. So, do we have any more? Thank you for the presentation. Okay, so many thanks to our presenters, guys. Thank you very much. Thank you all for participating. We hope that you found it interesting and inspiring. So I would also encourage you to join us on the next meetup that will take place on February next year. The topic would be a journey from on-prem to the cloud. So for further details, please follow us on LinkedIn and Facebook. Once again, thank you very much. Have a good rest of the day. Thank you, guys. Goodbye.